Aqueous solutions and solubility. So we mentioned aqueous earlier. An aqueous solution is a homogeneous mixture of a substance with water. When ionic compounds dissolve in water, they usually dissociate into their component ions, and they make a homogeneous solution. So when we talk about an aqueous solution, this is a homogeneous mixture, meaning it's the same throughout. We've talked about that before. Aqueous tells us that it's water. It's not dissolved in vegetable oil or something. So here's a picture of sodium chloride being dissolved in water. Table salt. You dissolve table salt in water, and it separates into its ions. You don't see any sodium chloride units floating around. It's all just sodium ions and chloride ions. So we say it dissociates. When people associate, they come together, and when you dissociate, you go apart from each other. The ions dissociate. And a substance that dissociates completely is called a strong electrolyte. So if we look at this illustration, here we have a glass of water, a battery, and a light bulb. The light bulb is not on because these two ends of the wires are not connected to each other. In order for the light bulb, that's a light bulb. In order for the light bulb to light, there has to be a flow of electric current. Electric current is electrons moving. And the electrons can't flow in a loop here because there's this gap. If we throw some salt into the water and don't change anything else, the light bulb turns on. It's really kind of amazing. Why? Well, now these charged ions can carry the current from one end of the wire to the other, and this solution will conduct electricity. And the light bulb will glow strongly. So these are called strong electrolyte solutions because they conduct electricity well. And a student this morning asked, is that the same electrolytes that they talk about, when you've been working out and you need to replenish your electrolytes? And they say, well, Gatorade, it's got electrolytes in it. Yes, it's the same sort of meaning. It's an ionic compound that's soluble in water. Your body needs sodium ions and potassium ions and chloride ions and a few other ions in order to function correctly. When you sweat profusely, you lose some of those ions. And drinking just plain water is not going to replenish those. If your potassium or your sodium levels get too low, you will die because your heart will stop beating. There are electrical processes that happen in your body that are necessary for life. And so you need these electrolytes in your body. So electrolytes are just soluble ionic compounds. Let's look at what happens when silver nitrate dissolves in water. Well, silver nitrate also is a strong electrolyte. It dissociates. But the two ions, yes, question?
So just plain water doesn't conduct electricity?
Plain water does not conduct electricity well. If you go to a high enough voltage, it will conduct, but only because it's decomposing. Pure water doesn't conduct electricity well at all. I know that kind of flies in the face of keeping your feet out of water when you're around electricity and stuff. The thing is, though, like a lake, is that pure water? No. Even tap water is not pure water. If you've got puddles on the ground and you're dealing with electric cords and stuff, is the water on the ground pure water? No. It's in contact with the dirt. There's probably some dissolved ionic compounds, some electrolytes in it. And so that's why in everyday life you want to avoid mixing electricity and water. But pure water doesn't conduct electricity. So silver nitrate, we've got nitrate ions and silver ions. Nitrate ions are polyatomic ions. We talked about those as being like bundle packs. They're shrink wrapped together. They stay intact. The nitrate ions do not dissociate from each other or come apart. They stay nitrate ions. They just dissociate from the silver ions. So we talked about ionic compounds when we talked about nomenclature as containing two different ions. And when they dissolve in water, they dissolve into two ions. One or both of them can be polyatomic. There are compounds that contain more than two ions, but we're not going to talk about them in this class. So in this class, it's always just two ions. So polyatomic ions dissolve as intact units. Not all ionic compounds dissolve. If we put silver chloride in water, it just sits as a lump in the bottom. And no matter how much you stir it, it will not dissolve. It's like, well, how is that different from sodium chloride? Well, it's different enough. It doesn't dissolve. It just doesn't. So we say a compound is soluble in a particular liquid if it dissolves, if it dissociates into ions. And it is insoluble if it doesn't. Sits there like a lump. How do we know? Well, we know through a set of empirical rules. Empirical means derived from experiment. So people did experiments. They took some sodium chloride and they put it in water and stirred it up. Yep, that dissolves. Let's take some silver chloride, put it in water, stir it. That doesn't dissolve. Lots of tests like that give rise to solubility rules. So here's the way your book presents the solubility rules. You do not need to memorize these, and I will not, you don't need to write them on your 3x5 card either. I will give these to you on an exam if you need them. So let's look at how this works. So the top part of this table, these are compounds. If they contain these ions, they're mostly soluble. So you look at your compound. If it's got lithium, sodium, potassium, or ammonium ion in it, it's soluble except nothing. No exceptions. If it's got nitrate or acetate ion, no exceptions, it's soluble. If it's got chloride, bromide, or iodide ion, it's soluble except if one of those ions is paired with silver, mercury, or lead. Those are insoluble. Sulfate compounds are soluble except for those guys. The bottom, these guys are insoluble with some exceptions. So if you've got lithium, sodium, potassium, or ammonium, it's going to be soluble. If you've got sulfide, with these guys, it's soluble. If you get hydroxide with these guys, calcium, strontium, and barium, it's slightly soluble. For our purposes, slightly soluble is the same as insoluble. It means that a little bit dissolves, but only a little bit. And so we're just going to go with two categories, soluble and insoluble. So slightly soluble, we're going to count as insoluble. And see what it says down here? For many purposes, these can be considered insoluble. Carbonate and phosphate, those guys are generally insoluble except with those. So let's look at how to use this table. Determine whether each compound is soluble or insoluble. So CUS. Go back and look at the table. We're going to look through here and we're going to look for copper ion and sulfide ion. And we don't find either of them up here. And here we find sulfide. Sulfide compounds are insoluble except, and we don't see copper as one of the exceptions. So that tells us that the copper sulfide is insoluble. So I'm going to just put an I there. Insoluble. Do you see how I did that? Iron sulfate, FeSO4. Two ions, iron and sulfate. We go looking for them in the table. So in the top part here, we don't see iron. Oh, here's sulfate. Sulfate compounds are mostly soluble except, oops, I don't know what I did there, except sulfate with strontium, barium, lead, or calcium. But we're looking at iron. Sulfate with iron is soluble. So I'm just going to write S for soluble. How about lead carbonate? Again, look at the table. We don't see lead or carbonate up here. We keep going. Oh, there's carbonate. Carbonate compounds are mostly insoluble. And then we look for an exception. Lead is not one of the exceptions. So lead carbonate, insoluble. How about ammonium chloride? Soluble or insoluble? Soluble. We look up here, first thing, ammonium. No exceptions. If we find the chloride, it's not going to contradict either. There are some exceptions, but ammonium isn't one of them. So ammonium chloride is soluble. Soluble. That's enough for today.